Hello, Mr. T here with another tutorial. Today I'll be giving a tutorial or lecture for calculus, and it will be introducing a new derivative rule that will allow us to find derivatives of much more complicated functions than we've been able to find so far. This rule builds upon the concept in algebra of composite functions. I've shown a simple example of a composite function here. So we have two functions, function f and g. F of u is defined here as u squared, and g of x is this linear function. And if we create a third function here, y, which is the composite of f and g, read as f of g of x, if we substitute for g of x, we've got 2x minus 5, so we're finding f of 2x minus 5. And if we substitute that expression in for the u, we get our function shown here. So this is the composite of those two functions. And what we want to be able to do for these composite functions is find the derivative. Now this is a simple composite, and we could find the derivatives using the rules that we've had so far. We would have to either FOIL out our problem or use this product rule here. So let's look at finding this function without using the new rule we're going to talk about today, and I'm going to show this in two ways. So first, we could expand this parentheses using the distributive property and simplify our function, and then apply using the sum and difference rule and our power rule, we could find our derivative. Alternatively, we recently learned the product rule, and we have two products here, two parts that are multiplied together, and we can use our product rule to find the derivative, and we get the same answer once we've simplified it. Now this would work when this is a power of 2. If this was a power of 3, 4, 5, or 6, this method would get very tedious foiling that out, and further, if this was a fractional exponent, we would not have a way of distributing that out. And if we tried using the product rule for a higher power, we have to use the rule kind of repetitively or in a recursive manner, and that would be quite difficult. So let's look if there's an easier way taking advantage of the power of composite functions. So if we look at the example we just had, we could write our function in composite notation. We showed that earlier. I just used now this notation here. If we use substitution property, putting in 2x minus 5 for this u, we have the same problem we worked on the last page. But we're going to take the derivative of each of these two functions separately. So if we find dy du using the power rule, we would get 2u. And if we find du dx using this equation, we have 2. Now let's look at if we multiplied these two derivatives together. So if we multiply these two fractions, the two du's cancel out, and we're going to be left with dy dx, which is what we were ultimately looking for. So if we apply that here, dy du was 2u, du dx is 2, and we multiply those together, we get dy dx, which is 4u. Now this is the derivative of that function we looked at in the earlier example. However, our answer is in terms of u, and we want our answer in terms of x. So we can substitute 2x minus 5 for u, and we get this 4 times what u was, and we distribute that out. We get the same answer that we had back on the earlier slide. So if I go back to the earlier slide, we've got the same answer there. This process is called the chain rule. So I hear that song in my head every time I work a problem using the chain rule. So In class, if we're working a problem that requires the chain rule and you forget to use it, I'm going to be reminding you of that song. Again, this was a fairly simple example we worked, but it's going to allow us to handle more complex functions, especially when we can represent those complex functions as a composite of two simpler functions that we know how to find the derivative of. So again, we are combining our substitution step with the derivative step, and we can write our chain rule as shown here. So we have here f of x being g of another function, and if we take the derivative, showing what we did before, we take the derivative of the g function and then we multiply it by the derivative of the u. Our u of x, when we look at problems in a minute, is going to be what I call the inner function. It's going to be the expression inside of a parentheses. And the f of x will be the outer function, which for our cases is generally going to be raising that parentheses to some sort of power. When we are finding the first step, when we find the derivative of this outer function, the g of x, we will treat the insides as an x, or as a single blob. So in our first step, we will not be taking the derivative of the inside. That comes in the second step. Hopefully this will become a little clearer as we go through a few examples. For our immediate use, we are going to be working with quantities or expressions that are raised to a power. So we're going to come up with a specialized version of the chain rule called the Generalized Power Rule. So this is one application of the chain rule. Later in our class, when we start looking at other functions like exponential functions and logarithm functions, we will be applying the chain rule there. And if you're taking AP calculus and we're using trig functions, the chain rule gets applied frequently there also. So let's look at a very specific version of the chain rule, which I'm calling the Generalized Power Rule. So this was our original power rule, and now when we have the chain rule, we've replaced x with some expression. I've called here u of x. So we've got some expression raised to a power. N could be negative, n could be positive, n could be a fractional exponent. And to compute the derivative, we are going to take this exponent times the constant out front, if there is one, just like up here. We're going to keep this expression or blob the way it is, and we are going to subtract 1 from the exponent, again as we did in the regular power rule. And then the chain rule part says we now have to take the derivative of the insides. We have to take the derivative of this expression and multiply it times this part which came from the power rule. We would then simplify that and have our final answer. So for the time being, since we're dealing with powers and polynomials and those kinds of expressions, this will be the format of the chain rule that we will be using on a regular basis. In our next slide, to wrap up this tutorial, we're going to show I'm going to show you 2 examples of using this generalized power rule. Okay, our first example is shown here, and to use the chain rule we're going to need to rewrite this. And let me use different colors here. So we've got some expression raised to the 1/2 power when I convert the radical to fractional exponents, and our expression, or as I called it in the PowerPoint slide, our u of x. So this is our g of x on the outside and our u of x in the middle. And if we want to take the derivative of this, we're going to use our generalized power rule that we just had. So let's look at finding that derivative. So f prime of x. And we are going to take this exponent and multiply it times our coefficient of 1. We are going to treat this as an x or a blob, so we're going to hold that the same. We're not changing that. We're not taking the derivative of that. We are subtracting 1 from our exponent. And now the chain rule says we now need to take the derivative of what was inside the parentheses and multiply that times this first part. So I've just applied the generalized power rule or the chain rule to take the derivative. Now all we're going to do is do some simplification. So this is a constant. We have times something and times something else. Multiplication is commutative, so we can multiply this 1/2 times this -2. So we get -1. And x, so -1x. And then I have 1 minus 2x to the -1/2 power. And I want to get rid of my negative exponent, so I'm going to move that to the denominator. So on the top we've got x, and on the bottom we've got 1 minus 2x to the 1/2 power. And we might put it back into radical notation since our original problem had radical notation, and our problem is complete. So this expression is the derivative of our f of x that we showed, that we started with. Let's look at another example, a second example. So here we have something. Now in this particular example, we could solve this using the quotient rule that we have just recently used, but I'm going to show you how to take the derivative using the chain rule. If this had had a parentheses around this with a power, then we would not be able to use the quotient rule, and we would be forced to use the generalized power rule. So I'm going to start out by rewriting our function here. So I took this to the numerator. So now we have something that looks like the generalized power rule. We have a constant. We have an expression raised to a power, to the nth power. So let's apply the generalized power rule, the chain rule here. When you see this, you're going to want to start hearing Aretha Franklin in your ear telling you to use the chain of rules, chain of fools. So let's go here. -1 times 3 is -3. Keep our expression, our blob, unchanged. Subtract 1 from the exponent, and now multiply by the derivative of what's inside the parentheses. We can now multiply this and this together to simplify. So we have -6x times x squared plus 1 to the -2 power. We will finish our problem by getting rid of our negative exponent by moving that expression to the denominator and changing our exponent. So now we have our answer here. Again, this would be, in my opinion, significantly easier than having to apply the quotient rule to this expression. So good luck as you chain away.